Hello everyone. Let's continue with our discussion on the anisotropic medium. So far we understood what are all the implications of having anisotropy. So how the dielectric constant, the susceptibility influences light propagation. Let's now look at how one can utilize this first of all. But before understanding how one could utilize it, let's look at some of the important concepts in defining the optical accesses and light propagation in this anisotropic medium. So the way that we do this is by taking the crystal, the material crystal, and then defining the accesses, right. So the coordinate system that we all are comfortable with, the Cartesian coordinate system x, y, z, right. So it is a 3-dimensional space, and then we are going to convert that into something optical. So when you move along z, when you move along x, and when you move along y, so how the optical constant of this material is going to change. So by definition, right, we saw anisotropy. So that means the material is not uniform with respect to space. So there could be change in the refractive index, right, when you go along x or when you go along y, right. So based on the direction of propagation, your light is going to experience a difference. So we need to understand how to define this optical accesses. So we know simple coordinate system, but then how do we translate that into optical accesses and understand the implication of those optical accesses on the light propagation, right. So particularly we will look at how the polarization will be affected, and if a light has a mixed polarization, what will happen to that propagating light. So those are all the things that we are going to look at in this section. So let's go back and then look at how we can understand this. So we need to define the optical accesses of the material. So a simple system is something that we all know of. This Z, can define this as x and this as y, right. So when we say anisotropy, right, the anisotropy can be of different kind, right. So anisotropy just tells us that there is some direction dependent property change. So that is all we understand. But in which direction we can't say, right. For example, you could have a system where n x and n y are equal, but it is not equal to n z, let us say, right. So in this particular case, the material is anisotropic, right. By definition it is anisotropic. The reason for that is not all three are same. So when you say isotropic, this is what isotropic means, but then this is anisotropic, right, by definition. But then if a light is propagating along z, right, along the z direction here, if the light is propagating through this axis, that means your electric field is between x and y, right. So if it is propagating through z, your field is between x and y plane. But when the light is propagating through this particular medium, by definition it is anisotropic, right. But then when the light is put along z axis, it will not feel anisotropy at all. The reason for that is your refractive index along x and y. So that is where your electric fields are going to be distributed, right, between x and y. So that electric field will not see any difference. So the light will feel this medium as if it is isotropic, right. So it is very important to understand the situation where the material anisotropy will affect the light propagation, right. So, you need to define the directions and so on, that is why defining optical axes are different. Okay. So, the moment I said okay nx ny is equal, right. So, the light that is propagating along z direction will not have any anisotropy effect. But then the moment I said x and y, right, it is in xy plane, then you would have already guessed that the polarization of light becomes very important here. So, whether the light is Ex polarized or Ey polarized, right. In this particular case it does not really matter because Nx equals Ny. So, let us take a scenario where Nx is not equal to Ny. In this case the light that is propagating will experience anisotropy, right. So, normally we define this through giving principal axes. So, let us look at what that is, right. So, optical axis, what is optical axis? Axis of a crystal. So, what is this? So, optical axis of a crystal is nothing but a unique axis, right. It is a unique axis in a crystal along which wave can propagate with an refractive index, wherein with an index of refraction that is, this is very important, that is independent of its polarization direction. Alright, so this is how we define optical axis of a crystal. So, optical axis of a crystal is a unique axis. So, it has to be unique axis in a crystal along which the wave can propagate. So, the wave can propagate, right, with an index that is independent of its polarization direction. So, this is how we define an optical axis. So, we cannot randomly choose any orientation. That is a big difference between choosing a coordinate system to represent a crystal, right. So, when you take a crystal, so you take all these atoms here and perhaps, and you will use the position of this atoms and then the orientation in order to define okay whether this is x, y, and this is z direction and so on, right. So, this is rather physical in nature, but when it comes to optical axis, our definition is slightly different. It is not any axis, it is a unique axis that has an index of refraction or refractive index is independent of the polarization of light that is propagating through. And when we define this, we have different axes. You have three systems here, x, y, and z, right. And if you have only one distinct principal index, let us say, right. So, we call that uniaxial crystals. So, what is uniaxial crystal? You only have one distinct principal axis or principal index, let us say, alright. So, principal index among three principal axes, alright. So, it has only one distinctive principal axis. We call this as a uniaxial crystal. alright, only one. So, this material is still anisotropic, okay. In any anisotropic crystal, right, I should say an anisotropic crystal, right, only one distinct principal axis, principal index among 3 principal axes. So, this is how we can define the uniaxial crystal, right. So, you do not have distinct indices in other directions, okay. So, normally this unique direction, right, the principal axis, we take Z as the unique principal axis. Normally Z is normally represented as a unique principal axis. All right. So, now let us look at, once we given unique axis Z, right, the identical principal indices of the refraction, they are called ordinary and extraordinary, right. So, once we have given define this Z as the principal axis, we can now define the others, okay. So, now let us look at Nx, now Ny and Nz, right. So, Nz is what we call the extraordinary index, right. This is extraordinary index. Both Nx and Ny, we call this as ordinary index. So, we can call this as N naught and this is Ne, alright. So, the crystal will have positive uniaxials, this is positive uniaxial, we call this as positive uniaxial if Ne is greater than N naught. We call this as negative uniaxial if Ne is less than N naught, right. So, based on the refractive index along the principal axis here, that is Az, right, you can define either it is positive uniaxial or negative uniaxial, alright. So, here you have to go back and look at the definition here. There is only one distinct principal index here, right. There is only one that is different from the other, right, because Nx and Ny are equal, let us say in this case, only Nz is different, right. So, the ordinary and extraordinary here is reasonably easy to understand, but there are crystals where we could have 3 distinct indices, right. So, Nx, Ny, Nz all are different. So, then life is going to be even more interesting, okay. So, you have all these unique coordinates here, okay. So, then we call that as biaxial crystal. So, in uniaxial we only had one unique principal axis, in biaxial we have 3 distinct, right. So, you have 3 distinct indices of refraction. And out of this we have 2 optical axis, right, and then we have one principal axis, okay. So, that is Z, right, and none of these 2, right, will coincide with any of the other principal axes here, right. So, that is what this biaxial crystals are about, right. So, they are all unique in nature, okay. So, once we have this ordinary and extraordinary planes that we defined, we can also understand try to understand how light would propagate, right, in this coordinate system. Okay. So, let us try to understand. We call those as ordinary and extraordinary waves. All right. So, in a linearly polarized wave, okay, the two normal modes, right, could exist both in ordinary wave or an extraordinary wave. Okay. So, let us look at what is an ordinary wave, and then we will look at extraordinary wave. All right. So, ordinary wave is nothing but the wave where the polarization, right, is perpendicular to the optical axis. So, here the polarization is perpendicular to the optical axis. All right. So, this is called an ordinary wave, and we use E naught for this. And here the polarization is perpendicular to E naught here. So, here this is the polarization is actually perpendicular to E naught. So, this is E E. So, this is your extraordinary wave. Right. And here the direction of these waves, right, when we say direction of polarization, we primarily mean the E, right, the electric field E here, and the direction of this this D, right, is also very important, that we will just shortly see. Okay. So, the easiest form to write this is E naught is parallel to D naught, which is parallel to E naught, right. So, for an extraordinary wave, so your E E will be parallel to D E, but not parallel to E E, right. So, this is something that you should try to understand. So, both E naught and E E being the unit vector. So, they are nothing but unit vectors of D naught and D E, right. So, that is why they are are perpendicular to the direction of propagation here. So, that is why they are parallel all the time, but they are perpendicular to the propagating vector, right, or propagation constant direction of propagation, that is k. Right. So, for a uniaxial crystal, let us try to map this, right, how one can understand this. Let us say this is Z and let us say this is Y. All right. So, an ordinary wave, so this is say X. So, your ordinary wave is here. Let me pick a different color. So, this is your ordinary wave that is having an angle phi, right, and then you have an extraordinary wave, that is Z, and this has an angle theta to this, and we all know that it is the propagation direction k here, and this is, and this angle is again theta. All right, and this is perpendicular. This angle which is between this is nothing but again phi. All right. So, this is phi. Let me take this out. This is phi. All right. So, this is for a uniaxial crystal with the optical axis Z, right. So, this is nothing but uniaxial crystal with optical axis along z. All right. So, now the unit vector E naught, as you can see, you can write it as sin theta k times z cap, right. So, that is hat, and we all know one can write it this way, right. So, both the ordinary and so this is extraordinary, ordinary and extraordinary wave can be found if both k and the optical axis are known, right. So, if you know the k, right, and if you know the direction, the optical axis, then we should be able to find E and E naught, all right. So, that is rather straightforward. So, let us look at a little bit more here, how you can use this to understand the two waves here. So, let us take a plane. So, this is your optical axis, z here, right, and then you have another for ordinary optical axis z. So, we have O wave, let us say, and let us say this is E wave. So, now for O wave, right. So, this is, so E is parallel to D, right, but then perpendicular to here, and it makes an angle theta, and this is your K, right, and this is our H. But then if you look at the extraordinary wave, the direction of propagation is all fine, this is again the same, but then the electric field, right, is in this way, right, and you can see D is not parallel. So, it has a certain angle to it. Okay. So, extraordinary waves has a vector D that is normal to K. So, this is the D is normal to K and lies in KZ plane, but E is not parallel to D in a extraordinary configuration. In an ordinary wave configuration, both E and D are parallel, right, and H is perpendicular to your K, right. So, that is something that we should keep in mind when we are talking about ordinary and extraordinary waves in a uniaxial crystal, right. So, let us move on and then see what happens if you have a more interesting biaxial crystals, or the refractive index of nx and ny that we saw here are equal, but then let us look at a situation where you have 3 different refractive indices, right. So, we call that as double refraction, right. So, let us look at material where you have 2 modes or 2 different refractive indices, right. So, we call that as material with birefringence, right. So, birefringent material. So, birefringence is nothing but it is an anisotropic medium that supports 2 distinct axes where you could have 2 different phase velocities, for example, right. So, if the light is moving in x and y, right, so you have nx and ny, so you have nx is not equal to ny. So, this will eventually result in let us say speed of light is going to be different here. So, n over nx and n over ny now. So, because of this 2 different phase velocities, you have 2 different refractive indices, which causes 2 refracted waves, right, and and the polarization of your electric field, whether you are in Ex or Ey that we discussed earlier, will have a very strong interaction and effect on this wave propagation. All right. This effect of having two refraction, right, it is called birefringence, or you call it as double refraction. So, either you call it as birefringence or double refraction, both are necessarily the same. So, now let us look at the field vectors that we introduced in an anisotropic medium. So, we can take DE this direction. So, light propagating here. So, the pointing vector S is here, and then the perpendicular is H and B, right. So, this is ordinary configuration. So, why we call it as ordinary? The propagation direction is where the wave is propagating through. So, K is the propagation here, S is the pointing vector, right. So, where the energy is going, right. So, let us look at the extraordinary case here. So, this is K, right. So, this is D and you have H and B will not have any effect, but we already know from our earlier understanding E and D are not going to be parallel. So, you will have a certain angle to your E. So, they are not going to be the same direction. So, because we have E, right, having not aligned with the principal axis here, what you expect to see, so this is O. So, what you expect to see is your K, right, or sorry, your pointing vector will have again an angle alpha with respect to the direction of propagation. So, now you can see the direction of propagation is along this, right, K, right. In other words, you can also call this as Z if that is giving you some imagination here. So, the direction of propagation is along this Z, right, but then look at the energy. So, the energy is not flowing in the direction of propagation. So, the energy is now propagating at a certain angle alpha, it is deviating from the actual propagation direction. All right. So, this is something very interesting, right, and this could give rise to some interesting application. So, one can exploit this angle with respect to your principal axis to create polarization dependent propagation. So, okay. So, let us look at what that is, right. If the electric field of an extraordinary wave is not parallel to the principal axis, right, if it is not parallel, its pointing vector will not be parallel to its propagation direction. That is what we are trying to say. All right. So, the energy is going to go away from the direction of its wavefront propagation. So, to summarize this, right, the energy flow flows away from the direction of its wavefront propagation. All right. So, this phenomena of moving away from the direction of propagation is called spatial walkoff. Spatial beam walkoff or spatial walkoff. Okay. Because it is moving away, right. So, if this particular separation happens in an anisotropic crystal, then the optical waves will split into two different beams, right. One of the one in along the propagation direction, one coming out at a certain angle alpha, right. So what will be that alpha is the question here, all right. So let's look at how one can arrive at this particular alpha. Again, I'll go to this similar to what we saw in for the uniaxial crystal. Let us look at the spatial walkoff in this birefringent material. So we can take this as xy plane, okay. So you have that. So this is your NE, all right. In this case, NE is less than N naught, let's say, right, and we have extraordinary here and DE here, and it has, as I mentioned, so here we have S ordinary and this is S extraordinary, all right. So KE and K naught are all same, so they are the same line. So this is nothing but theta that we have, and this is our alpha. So the same thing here, this is theta and this is alpha, right, and the angle between this N naught, that is what we have, and our E is psi E, right, and here this angle that we have is psi, same thing, right, and this is nothing but your D naught, which is parallel to E naught. So this is the condition when the extraordinary refractive index is less than N naught, all right. So if we take another scenario where your N naught is less than Ne, right. So the positive and negative uniaxial crystal, we saw that, right. So here the situation slightly changes, good xy plane here, again you have Z and extraordinary is here, and then we have SE and then SO. So here K naught KE along the same line. So here this is theta, right, and this angle now is alpha, and this is nothing but chi E, all right. So now since we have moved this way, you have DE and then we have EE, again same thing. So chi E here, so this is theta and then this is alpha, and here D naught to E naught, all right. So this is positive and negative crystal planes that you can have, whether it is Ne is greater or N naught is greater, all right. So this gives us how our electric field is oriented with respect to the crystals that we talked about. Now one can actually find the walkoff, right. So the angle alpha between SE, right, and K. So SE and K, which is defined as alpha, right. So that alpha, so this is angle between SE and K, right. So alpha is nothing but psi E minus theta, right. So this is what we call walk-off angle, right. We saw this alpha here, right. So how far this energy is going to deviate from where you from the propagation direction. So, that is our alpha. So, alpha is also angle between EE and DE, right. So, alpha is nothing but angle between DE and EE. So, let us look at what this actual alpha is, right. So, this is nothing but tan inverse of n naught square by n e square tan theta minus theta. So, your psi e is nothing but tan inverse of n naught square over n e square times tan theta. Okay. So, let me write it again, tan theta. All right. So, this should give us how far the spatial walkoff will be, right. So, why this is interesting? Why are we interested in understanding this deviation? We can actually exploit this difference, right, in the propagation direction for polarization splitting, right. One interesting application is so polarization beam splitter. So, what a simple block diagram would be. So, I have waves that are polarized in a certain way, right, and when I go through this based on the angle, right, at which I hit, right, I could have a light that is passing through, right, that is the ordinary, right. So, that is S naught, and then I could also have a light that is coming out, that is S extraordinary, right. So, you will have this splitting of this, right. So, this is the polarization beam splitter, right. At what angle it is going out is basically defined by the alpha that we just saw. All right. So, it has to move a certain distance L, right, in order to do this spatial movement, but based on the length you can spatially segregate these two waves separately. So, this is used in lot of quantum photonics implementation of lot of gates and information processing, where you want to take a photon and then you want to split it, right. So, you have a bunch of photons coming in with a certain polarization, right, and you want to split it. So, how do we split it is by using this particular technique of spatial splitting, right, and the wave fronts are coming here, right, and in this case it will be aligned in plane, and in this case maybe I should put it like this and like this, right. So, vertically aligned and also horizontally aligned. So, you can have waves like this, right. So, there are two polarization coming in and you can split this polarization based on this. So, how far you can split them, right. Let us say d is the distance between the two waves, right, and the distance between, or let us say beam separation is nothing but L tan alpha here. Okay. So, if you want them to be separated reasonably far enough, right, then you have to increase the interaction length, right. So, if you increase the length of interaction, we should be able to separate the two polarization. So, you will get this polarization here and get this polarization here. All right. So, this is how you can exploit the property of these anisotropic crystals for multiple applications. Okay. There are few specific crystals and geometries one can use based on the material, right. So you can you must have read something called Woolston prism is one, Rocon prism, and then the other one is some more famous Glenn Thomson prism. So all these prisms, prism configuration actually splits the polarization. For example, the WP, it's a prism configuration like this. So where you will get an ordinary wave here and extraordinary wave like this, and then in the other configuration again you would have ordinary wave here and then the extraordinary wave here, right. And in Glenn Thomson configuration, perhaps you must have done this in introduction to photonics or optics courses. So you have very large difference. So this is ordinary and this is extraordinary. All right. So this is Glenn Thomson at the bottom. Then you have Rocon, and then you have Woolston. Okay. So you can see here why Glenn Thomson is much popular. The reason for it is, I know there is a 90-degree shift, right, in the direction of propagation. So it's orthogonal. So when you are putting a beam splitter, polarization beam splitter, it works reasonably well when you are organizing your optics. So here you have to rely on the distance. So you have to put your detector or next optics far away to have the required spatial separation. But in Glenn Thomson prism, it's much simpler because it's inherent to it to divide the light, divide the polarization orthogonally. All right. So one can use this beam walkoff technique or phenomena in order to split the beam, and we saw what affects the splitting. It's primarily the difference in the ordinary and extraordinary refractive index. So the larger the difference, the better your splitting angle is, and you, for a compact device you should be able to have larger walkoff. All right. So with that we came to an end to this particular topic of understanding anisotropy in materials and how one can understand this anisotropy and use this anisotropy for our own good, various interesting application one can develop. But that's not the end. So we are going to use this in our integrated optical waveguides and devices and exploit these properties. All right. So right now we only saw the passive properties. So once you bring in the electro-optic properties of this material, it becomes even more interesting, which is something we will discuss later on in the other sections of this course. Thank you very much for listening.